Yeah, thank you very much for the introduction, and also thank you to all of the organizers for inviting me. It's a pleasure to be here. So I would like to talk about something which I call arithmetic counts of tropical plane curves and their properties. And what this is a story in enumerative geometry. Okay, so let me start by saying, let K be a field. So now I have algebraic geometry at my disposal, and I can phrase a So now I can phrase a problem, right? So I would like you to consider the following counting problem, which is very old, I guess, and I assume everybody has seen this in some version at some point in their lives. So given n equals the correct number, which is 3d plus g minus 1 points in general position, in the plane P2, then let me ask how many curves of genus G and degree D are there such that these curves pass through the points. So this is my setup, this is my problem. And yeah, as I said, this problem is very old, so there's already a lot of history to be told, which I'm not going to do because this talk is very short. But let me try and conceptualize what we actually mean with this problem. What are we actually looking for? So the goal in answering this question is really try and find invariance associated to this problem. Where the word invariant is supposed to refer to a quantity that is actually independent of the configuration of the points. Right? So I mean, a priori you would assume that if I choose some random points, then the answer to this quantitative question should depend on the exact points that I chose. But that's not what I'm interested in. We're interested in finding invariance, meaning things that are intrinsic to the problem as phrased, meaning depending only on the discrete data of degree D and genus G, and not on the exact configuration. Yeah, they always have to be in general position, yeah. So if my base field is the complex numbers, then as you should expect with algebraic geometry, everything is as nice as it gets. And in this case, we already have a wonderful answer to this counting problem, which is the Gromov-Witten invariance. And this is probably also the connection to the question as it is phrased. I mean, the question is how many curves are there? And you can see that in genus 0, these Gromov-Witten invariants are actually the number of curves as phrased. right? But already if you look at the complex case in higher genus, chromophitten invariants are no longer the exact number, but they are a bit more abstract, I would say. They are simply invariants that are associated to the problem. So what if we go to different base fields? Well, as you might expect, things get more complicated. And in fact, there has been very recent work which is kind of defining what is known to date. So this is work by Mark Levine, 2018. He came up with a set of invariants associated to this kind of problem, where the only assumptions are that the base field K should be a perfect field of characteristic not 2 or 3. Which is, I think, remarkably weak assumptions. And yeah, so what he defines is something that is fairly complicated, and something that I would like to call, for the purpose of this talk, the Levine-Velchanchet invariance. Which is basically because it generalizes some previous work by Velchanchet, who already managed to introduce invariance for this counting problem over the real numbers as base field. And what Mark Levine does is he generalizes this dramatically to allow for this fairly general setup here. And oh, okay, sorry, one more restriction. So far, this theory only works in genus 0, in the sense that only in genus 0 we have a proof that these quantities that are defined here are actually invariants. And maybe one more word on the idea behind this is that this uses input from what is called A1 homotopy theory, which I know nothing about. So this is not what I'm going to talk about for the rest of the talk, but rather I would like to give a different perspective on this material from my point of view, which is tropical geometry. So in short, from my perspective, tropical geometry is a theory that looks in some sense very similar to algebraic geometry, in the sense that it deals with similar concepts and similar questions. But the catch is that all the objects that we're studying, they are no longer defined by polynomial equations, but rather they are governed by combinatorics. And in this setting, in this kind of like shadow worlds that looks like algebraic geometry, but done in a completely different way, we can restate the original counting problem. And to do so, the first thing that we have to understand is, well, what is a plane tropical curve? So let me give you a very, very quick and sketch of a definition. A plane tropical curve is a list of adjectives, namely a parametrized, balanced, one-dimensional, rational, polyhedral complex in the plane, but now the plane is no longer some fancy projective plane, it's actually the real Euclidean plane. Okay, so let me try and put some life into all those words by drawing you a sketch as an example. it is something like this. Right? It's a one-dimensional polyhedral complex. I think we can see that. It's built from polyhedral cells, which in the one-dimensional case are simply intervals or unbounded rays. Right? So these guys here, they go off to infinity in those directions. It is rational in the sense that all the slopes of these things as embedded in the real plane are actually rational numbers. In the sense that, you know, here you got like a slope of 1, here you got like a slope of, you know, I mean, yeah. Get it, yeah, you got a slope. Okay, so we see one-dimensional. We can imagine rational. We got the word parametrized here, which means that I should be thinking of this picture as a graph being mapped into the plane, which allows me then to resolve certain uncertainties, like, for example, this guy over here. I already tried to indicate that this is not a vertex. This is a crossing where simply two branches of the abstract graph just happen to overlap in the image. So something like this is resolved by the word parametrized. And finally, there's the word balanced, which means that whenever you look at a vertex, like for example, this guy over here, if you sum up the primitive tangent directions of the outgoing, one simplices here, then, you know, up plus left plus down right gives 0. That's balancing. Well, I mean, there's something missing. You add the directions, you don't get 0. Okay, so these are my tropical curves, and what I can make sense of is now the words that I need to phrase this problem. Namely, I can define the genus of such a parametrized tropical curve to be the genus of the graph, the abstract graph, which I use for parametrizing the picture, which in this case, since I resolved this as two branches just happen to be mapped together and not a vertex, it doesn't have any non-trivial cycle. So in this picture, I would actually call this a genus 0 tropical curve. The second thing is degree, which is in a very, very, very rough way saying the number of infinite rays per direction. So you can see that there's 3 directions in which I have infinite rays going off. I've got some going off to the left over here. I've got some going down here, and I got some going up to the top right corner. And in each direction, I happen to have 3, which is I mean, yeah, okay. It's just a sketch of a definition. So this number 3 is the degree of the curve. So in other words, this is really a plane tropical cubic curve. Yes, please.
Do the rays, like the abstract graph, do the rays correspond with some vertex and infinity?
No, people typically use the formulation of legs on the graph. So the idea is to have certain half edges that are attached to only one vertex and there's nothing on the other end.
It is probably like a simple statement that the number of those infinite rays in each direction has to be the same, right? And it's probably connected with balance, right?
Well, it is in fact this is how okay, this is necessarily the case because you want to be modeling things in P2. And in some sense, the idea is that P2 is a toric variety, which is defined by this polygon. And the sides of these polygons, they all have the same length. And that's why if you want to model curves, tropical curves corresponding to algebraic curves in P2, you should have things that have their unbounded ends going out in these three directions and having the same number per direction because you want to be dual to this polytope. That's the bigger picture. Okay. So I gave you a sketch of a definition, and I gave you all the words that show up in the original algebra geometric counting problem up there. So what I can do now is I can rephrase the problem purely in tropical language by just putting the word tropical in front of the word curve, I guess. And if you do that, yeah. Oh, from the graph to the curve. Yeah, that's the hard direction. The other way, yeah, that's a bit easier. So in some sense, we saw in the first talk this morning these kind of degenerate broken curves that happen when you move to the boundary of the moduli space, where a smooth genus G curve degenerates into something, you know, if we go all the way, we've got this thing, whoa. We've got something like this as a very, very broken curve. And what you're supposed to do is build the dual graph of this thing, right? So the idea is we have two components here that you should take as your vertices, and then the nodal singularities you should take as edges, right? So this guy in the middle, this node here, connects the two components, whereas these nodes out here, they connect the component with itself, so I'm drawing them as self-loops. And this is kind of the first step to setting up the entire process of translating plane curves into tropical plane curves, because this gives you the kind of combinatorial type of the graph that you see here abstractly, right? And now you only have to, well, there's a lot to be done, because now you also have to include the embedding into the plane into this translation procedure. Yeah. Okay. Great. So as I said, we have now a combinatorial counterpart of the original counting problem up there. And this problem is completely solved, I would say. Essentially going back to Mikhalkin in his paper from 2005, where what he does is he defines what I'm calling the complex multiplicity of a tropical curve gamma. So gamma is the tropical curve. Such that we can define a quantity, which I'm calling n complex tropical, given by summing over tropical curves of genus G and degree D through n points. And for each curve, we're adding in the multiplicity of the curve. And if you do this, what you get is this quantity here, which Mikhalkin proved to be an invariant of the tropical counting problem. And moreover, it gets even better. This purely tropical answer to a purely tropical problem is in fact the Gromov-Witten invariant. So in some sense, Mikhalkin was not just solving a tropical enumerative problem in the sense that he managed to come up with an invariant, but he managed to do this in a very clever way, in a sense that it is related to the original algebra geometric counting problem by actually solving it in a purely combinatorial way. So what is really cool about this result is that the tropical problem is much easier to work with because it's just graphs, right? So in fact, the tropical approach allows you to compute chromospheric invariants that, I mean, maybe you didn't know how to compute them before, like practically. You can implement the computation of this quantity on a computer and have a computer do chromospheric invariants for you.
In this language, the endpoints, do they now appear on this real plane, or like they
Yes.
appear before the translation of the curve?
Yes. Yes. Endpoints in R2. Yes.
Is it possible to demonstrate in the case n equals 5, d equals 2, g equals 0 in a finite time? You know, classical, how many conics are there through 5 points? 1, right? Actually, I don't know.
Yeah, there's five conics through 1 point.
So is the same true in tropical world?
Yes, that's true. Yeah.
It's surprising because I thought the slopes can be whatever rational number they want. So this is real for something finite. Yeah.
Well, okay. So there is a limitation imposed by again, you wanting to model things that correspond to curves in P2 requires you to be dual to the Newton polygon, to this polygon defining P2 as a toric variety. So even though the slopes are rational numbers a priori, the fact that you're fixing the ends to be in the direction left, down, and upright, then by balancing imposes enormous restrictions on the slopes on the pieces in between.
Okay, and if you wouldn't mind, could you just draw such a geometrical curve? Sorry, since I know the combinatorics of this problem, let me tell you, maybe after the talk is over, if there's time, because otherwise we're going to sink track.
Okay, thank you. Okay, yeah, let me suggest to go the next step, because again, we have a beautiful theorem here that tells you that tropical geometry is powerful enough to solve an enumerative question from algebraic geometry. So I told you before that nowadays we have, oh no, it's gone. So nowadays we have the algebraic question pushed to arbitrary base fields with arbitrary characteristics. Is tropical geometry still good enough to do it? And the answer is yes, as was shown by Jaramillo Puentes and Pauli in, well, accepted this year, archived last year, I think, where they show that the ideas of Mikalkin can be generalized. So what they do is they define a new type of multiplicity, which I'm calling the A1 multiplicity of a tropical curve gamma, such that we recover the Levine-Belchanger invariance by a tropical curve count. And what is, I think, very notable is that this tropical curve count has a very familiar form, namely it's the same as I wrote over there. So we do a sum over the same things as before, but now we use the A1 multiplicity instead of the complex multiplicity by Mikalkin, which is beautiful because this sum, since it is the same as it is here, like it's the same in the sense that we're summing over the same curves. The problem hasn't changed. It's still tropical curves of genus 0, degree D, in R2, passing through the points. It is a sum that is already known and that has already been studied. And that is something that we have exploited in joint work to study properties of these brand new Levine-Welchanger invariants going through this statement.
How do I take points over an arbitrary field?
Well, I mean, over an arbitrary field, you still have P2, a projective plane. And now you can think of scheme theoretic points.
Yeah, if I take points, say, F2.
Yeah.
How do I move them from the finite field? How do I move them on?
Okay. So okay, so I was trying to suggest this procedure of passing from a smooth algebraic setting to the combinatorial setting, and you can see that it involves a degeneration. So what you should do for this process is you shouldn't imagine this point by itself, but in fact you should be imagining a degenerating family of curves as the input to this tropicalization procedure. And if you consider a family, then your base shouldn't be a field itself, right? This family as a scheme lives not over F2, but it lives over some formal power series extension of F2. And over that field, you've got more structure. For example, a non-Archimedean valuation. And that's what you use. Okay. So let me just finish by sketching some results, which is joint work with Jaramillo Puentes. God, the alphabet. Okay, I'm gonna mess up the alphabet. Markvik, Pauli, and myself. Archive here because nothing is accepted yet. We studied these tropical counts. Okay. And what we found is several properties. Number one, we can prove by purely combinatorial methods that the quantity itself is an invariant, which was already clear from the correspondence theorem up there and the original work by Mark Levine. But this is something that you can in fact see on a purely combinatorial level as well. So we give a combinatorial proof. Number two, this invariant can be computed recursively in a recursive procedure that is inspired by the Caporaso-Harris formula. Number three, I said before that the charming thing about this tropical approach to enumerative geometry is really that it allows for effective computation, also on a computer. And this is something that you can drive even further by actually simplifying this sum over tropical curves into a sum over combinatorial gadgets that combine many tropical curves that behave similarly into one object, and these objects are called floor diagrams. So what we've verified is that these brand new invariants can be computed effectively and efficiently where this is more of a heuristic thing and nothing that I can quantify, by using floor diagrams. And finally, let me say that these brand new arithmetic enumerative invariants satisfy certain piecewise polynomiality properties. Okay, and kind of the upshot is that we've proved all of this in a purely combinatorial way, simply by using that this sum over all tropical curves subject to the problem, that this sum is understood very well. This is something that we put into this, so all the proofs are essentially from scratch, even though in genus 0, we have a theorem that says that we can actually use algebraic input. We didn't use that. And for some things like the piecewise polynomiality properties, our results also induce new results in algebraic geometry because these properties have not been shown by the arithmetic community yet. So that's it. Thank you.